In Chapter 3, we're going to talk about the following concepts. We're going to talk about abstraction, modularisation, object creation, object diagrams, method calls, and the debug process. In the previous chapters, we've examined what objects are and how they are implemented. In particular, we discussed fields, constructors, and methods when we looked at class definitions. We shall now go one step further. To construct interesting applications, it's not enough to build individual working objects. Instead, objects must be combined so that they cooperate to perform a common task. So in this chapter, we shall build a small application from 3 objects and arrange for methods to call other methods to achieve their goal. And the project we shall use to discuss interaction of objects is a display for a digital clock. The display shows hours and minutes separated by a colon, as can be seen here. For this exercise, we shall first build a clock with a European-style 24-hour display. Thus, the display shows the time from 00:00, which is midnight, to 23:59, which is 1 minute before midnight. It turns out, on closer inspection, that building a 12-hour clock is slightly more difficult than a 24-hour clock, so we're going to leave this until the end of the chapter. A first idea might be to implement the whole clock display in a single class. That is, after all, what we have seen so far, how to build classes to do a job. However, here we shall approach this problem slightly differently. We will see whether we can identify subcomponents in the problem that we can turn into separate classes. The reason is complexity. As we progress in this book, the examples we use and the programs we build will get more and more complex. Trivial tasks, such as the ticket machine, can be solved as a single problem. You can look at the complete task and devise a solution using a single class. But for more complex problems, that's too simplistic, because as a problem grows larger, it becomes increasingly difficult to keep track of all the details at the same time. The solution we use to deal with the complexity problem is abstraction. We divide the problem into subproblems and then again into sub-subproblems and so on until the individual problems are small enough to be easy to deal with. And once we solve one of those subproblems, we don't think about the details of that part anymore, but treat the solution as a single building block for the next problem. And this technique is sometimes referred to as divide and conquer. Let's discuss this with an example. Imagine engineers at a car company designing a new car. They may think about the parts of the car, such as the shape of the outer body, the size and the location of the engine, the number and the size of seats in the passenger area, the exact spacing of the wheels, and so on. Another engineer, on the other hand, whose job is to design the engine, think of the many parts of an engine. For example, the cylinders, the injection mechanism, the carburetor, the electronics, etc., etc. They will think of the engine not as a single entity, but as a complex work of many parts. And one of these parts may be a spark plug. Then there's an engineer, maybe in a different company, who designs the spark plug. He will think of the spark plug as a complex artifact of many parts. He might have conducted complex studies to determine exactly what kind of metal to use for the contacts, or what kind of metal and production process to use for the insulation. The same is true of many other parts. A designer at the highest level will regard the wheel as a single part. Another engineer, much further down the chain, may spend her days thinking about the chemical composition necessary to produce the right materials to make the tyres. For the tyre engineer, the tyre is a complex thing. The car company will just buy the tyre from the tyre company and then view that as a single entity. And this is abstraction. The engineer in the car company abstracts from the details of the tyre manufacturer to be able to concentrate on the details of the construction of, say, the wheel, and the designer designing the body shape of the car abstracts from the technical details of the wheels and the engine to concentrate on the design of the body, as He will just be interested in the size of the engine and the wheels. The same is true for every other component. While someone might be concerned with designing the interior passenger space, someone else may be working on developing the fabric that will eventually be used to cover the seats. The point is, if viewed in enough detail, the car consists of so many parts that it is practically impossible for a single person to know every detail about every part at the same time. And if that were necessary, no car could ever be built. The reason why cars are successfully built is that engineers use modularization and abstraction. They divide the car into independent modules, such as the wheel, engine, gearbox, seat, steering wheel, etc., etc. And they get separate people to work on the separate modules independently. When a module is built, they use abstraction. They view that module as a single component that is then used to build more complex components. Therefore, modularization and abstraction complement each other. Modularization is the process of dividing larger things, or otherwise known as problems, into smaller parts, whilst abstraction is the process of ignoring the details to focus on the bigger picture. The same principles of modularization and abstraction discussed in the previous section are used in software development. To help us maintain an overview of complex programs, we try to identify subcomponents that we can program as independent entities. Then we try to use these subcomponents as if they were simple parts, without being concerned about their inner complexities. In object-oriented programming, these components and subcomponents are objects. If we were trying to construct a car in software using an object-oriented language, we would try to do what car engineers do. Instead of implementing the car as a single monolithic object, we would first construct separate objects of an engine, gearbox, wheel, seat, and so on, and then assemble the car object from those smaller objects. Identifying what kinds of objects, and with these classes, you should have in a software system for any given problem is not always easy, and we shall have a lot more to say about that later in the book. But for now, we shall start with a relatively simple example. Now, back to our digital clock. So let's have a closer look at the clock display example. Using the abstraction concepts we have just described, we want to try and find the best way to view this example so that we can write some classes to implement it. One way to look at it is to consider it as consisting of a single display of 4 digits, 2 digits for the hours and 2 digits for the minutes. If we now abstract away from that very low-level view, we can see that it could be viewed as 2 separate 2-digit displays, which are 1 pair for the hours and 1 pair for the minutes. One pair starts at 0 and increases by 1 each hour, and then rolls to 0 after reaching its limit of 23, and the other rolls back to 0 after reaching its limit of 59. The similarity in behavior of these 2 displays might then lead us to abstract away even further from viewing the hours display and the minutes display distinctly. Instead, we might think of them as being objects that we can display values from 0 up to a given limit. The value can be incremented, but if the value reaches a limit, it rolls over to 0. So now we seem to have reached an appropriate level of abstraction that we can represent as a class, which would be a 2-digit display class. And for our clock display, we shall first program a class for a 2-digit display, as shown here, and then give it an accessor method to get its value, and 2 mutator methods to then set the value and to increment it. And once we've defined this class, we can then just create 2 objects of the class with different limits to construct the entire clock display. As discussed previously, in order to build the clock display, we will first build a 2-digit number display. And this display needs to store 2 values. One is the limit to which we can count before rolling over to 0, and the other is the current value. and we shall represent both of these as integer fields in our class. We shall look at the remaining details of this class later. But first, let's assume that we can build the class NumberDisplay, and then let's think a little bit more about the complete ClockDisplay. And we would build the complete ClockDisplay by having an object that has internally two number displays, one for the hours and one for the minutes. Each of the number displays would be a field in the ClockDisplay. And here we can make use of a detail that we've not mentioned before. That is, classes define types. When we discussed fields in Chapter 2, we said that the word private in the field declaration is followed by a type and a name for that field. But here, we use the class NumberDisplay as the type for the fields named hours and minutes. And this shows that class names can be used as types. The type of a field specifies what kinds of values can be stored in the field. If the type is a class, then the field can hold objects of that class. But declaring a field or another variable of a class type does not automatically create an object of that type. Instead, the field is initially empty. We do not yet have a NumberDisplay object. The associated object will have to be created explicitly, and we shall see how this is done when we look at the constructor of the ClockDisplay class. The structure described in the previous section, one ClockDisplay object holding two NumberDisplay objects, can be visualized in an object diagram as shown here. In this diagram, you see that we are dealing with three objects. And here, we see the class diagram for the same situation. Note that the class diagram only shows two classes, whereas the object diagram shows three objects. This has to do with the fact that we can create multiple objects from the same class. And here, we can create two NumberDisplay objects from the NumberDisplay class. And these two diagrams offer different views of the same application. The class diagram shows the static view. It depicts what we have at the time of writing the program. We have two classes, and the arrow indicates that the class ClockDisplay makes use of the class NumberDisplay. NumberDisplay is mentioned in the source code of ClockDisplay. We also say that the ClockDisplay depends on the NumberDisplay. To start the program, we will create an object of the class ClockDisplay. We will then program the ClockDisplay so that it automatically creates two NumberDisplay objects for itself. Thus, the object diagram shows the situation at runtime, where the application is running. This is also called the dynamic view. The object diagram also shows another important detail. When the variable stores an object, the object is not stored in the variable directly, but rather an object reference is stored in the variable. In the diagram, the variable is shown as a white box, and the object reference is shown as an arrow. And the object referred to is stored outside of the referring object, and the object reference links the two. It is very important to understand these two diagrams and the different views. BlueJ displays only the static view, and you can see the class diagram in its main window. But in order to plan and understand Java programs, you need to be able to construct object diagrams on paper or in your head. When we think about what our program will do, we think about the object structures it creates and how these objects interact. Being able to visualize the object structures, therefore, is essential. Java knows two very different kinds of type: primitive types and object types. Primitive types are all predefined in the Java language. They include types such as int and boolean, and a complete list of primitive types is given in Appendix B. Object types, on the other hand, are those defined by classes. Some classes are defined by the standard Java system, such as string, whereas others are those classes that we write ourselves. Both primitive types and object types can be used as types, but there are situations in which they behave differently. One difference is how values are stored. As we can see from our diagrams, primitive types are stored directly in a variable, where we have written the value directly into the variable box, for example, as we saw in chapter 2, whereas objects, on the other hand, are not stored directly in the variable, but instead a reference to the object is stored. And this is drawn as an arrow in our diagrams, as we saw before. And we will see further differences between primitive types and object types later on. So before we start to analyze the source code of the full ClockDisplay project, it will help if you gain an understanding of the NumberDisplay class and how its features support the building of the ClockDisplay class. This can be found in the separate NumberDisplay project. And here we see the complete source code of the class NumberDisplay. Overall, this class is fairly straightforward, although it does illustrate a few new features of Java. It has the two fields that we discussed previously, one constructor and four methods, which are getValue, setValue, getDisplayValue, and increment. So why not take a bit of time to explore this class, play around with some of the methods, and have a go at some of the exercises shown on the screen here. Okay, so now that you've had a chance to play around with this NumberDisplay class, let's continue. So the constructor receives the rollover limit as a parameter. If, for example, 24 is passed in as the rollover limit, the display will roll over to 0 at that value. Thus, the range for the display value would be 0 to 23. And this feature allows us to use this class for both the hour and minute displays. For the hour display, we will create a number display with the limit 24, and for the minute display, we will create one with the limit of 60. The constructor stores the rollover limit in a field and then sets the current value of the display to 0. Next follows a simple accessor method for the current display value, which is the getValue method. And this allows the other objects to read the current value of the display. The following sections discuss some new features that have been used in the setValue, getDisplayValue, and increment methods. The following method setValue is interesting because it tries to make sure that the starting value of a number display object is always valid. And we see the method shown here. And so here, we pass the new value for the display as a parameter into the method. However, before we assign the value, we have to check whether the value is legal. The legal range for the value, as discussed previously, is 0 to 1 less than the limit. So we can use an if statement to check that value is legal before we assign it. The symbol ampersand is a logical AND operator. It causes the condition in the if statement to be true if both of the conditions on either side of the ampersand symbol are true. And refer to Appendix C if you wish to see a complete table of logic operators in Java. So logic operators operate on Boolean values, which remember these are true or false, and produce a new Boolean value as a result. The three most important logical operators are AND, OR, and NOT. And here we see the symbols as they're written in Java. The first expression shown here, which is A and B, is true if both A and B are true, and false in all other cases. The second expression shown here, which is A or B, is true if either A or B or both of them are true, and false if they are both false. And finally, the third expression shown here, which is not A, is true if A is false and false if A is true. So to test your understanding of these logical operators, why not have a go at some of the exercises shown here? See if you can work out the result of these expressions. Which of these expressions will result with true, and which ones will result with false? The next method, getDisplayValue, also returns the display's value, but in a different format. The reason is that we want to display the value as a 2-digit string. That is, if the current time is 3:05 AM, we want it to read 03:05, not 3:5. To enable us to do this easily, we've implemented the getDisplayValue method, and this method returns the current value as a string, and it adds a leading 0 if the value is less than 10. And here we see the relevant section of the code. Note that the 0 is written in double quotes, or speech marks. Thus, we have written the string 0, not the integer number 0. Then, the expression 0 plus value adds a string and an integer, because the type of value is an integer. And in this case, the plus operator represents string concatenation again, as we saw in the previous chapter. But before continuing, let's look at the string concatenation a little more closely. The plus operator has different meanings, depending on the type of its operands. If both operands are numbers, it represents addition, as we'd expect. Thus, 42 plus 12 adds those two numbers, and the result is 54. However, if the operands are strings, then the meaning of the plus sign is string concatenation, and the result is a single string that consists of both operands stuck together. For example, the result of the expression Java plus with BlueJ is a single string, Java with BlueJ. But note that the system does not automatically add a space between strings. If you want a space, you have to include that yourself within one of the strings. If one of the operands of a plus operation is a string and the other is not, then the other operand is automatically converted to a string, and then a string concatenation is performed. Thus, answer plus 42 results in the string answer 42. And this works for all types. Whatever type is added to a string is automatically converted to a string and then concatenated. So back to our code in the getDisplayValue method. If value contains 3, for example, then the statement return 0 plus value will return the string 03. But in the case where the value is greater than 9, we've used a little trick. We've said return empty string plus value. Here, we concatenate value with an empty string. The result is that the value will be converted to a string and no other characters will be prefixed to it. We're using the plus operator for the sole purpose of forcing a conversion of the integer value to a value of type string. The last method in the NumberDisplay class increments the display value by 1. It takes care that the value resets to 0 when the limit is reached, as we can see here. This method uses the Modulo Operator, which has the percentage sign symbol, and the Modulo Operator calculates the remainder of an integer division. For example, the result of the division 27 divided by 4 can be expressed in integer numbers as the result being 6 and the remainder being 3. And the modulo operator returns just the remainder of such a division. Thus, the result of the expression 27 modulo 4 would be 3. Now that we've seen how we can build a class that defines a 2-digit number display, we shall look in more detail at the ClockDisplay class, the class that will create 2 number displays to create a full-time display. And here we see the complete source code of the ClockDisplay class, which can be found in the ClockDisplay project. In this project, we use the field displayString to simulate the actual display device of the clock. Were this software to run in a real clock, we would present the output on the real clock display instead. So this string serves as our software simulation for the clock's output device. In addition to the display string, the ClockDisplay class has two more fields, which are hours and minutes. Each can hold a reference to an object of type NumberDisplay. The logical value of the clock's display, which is the current time, is stored in these NumberDisplay objects. And we see here an object diagram of this application, where the current time is 15:23. The first question we have to ask ourselves is, where do the NumberDisplay objects used by the ClockDisplay come from? As a user of ClockDisplay, when we create a ClockDisplay object, we assume that our ClockDisplay has hours and minutes. So by simply creating a ClockDisplay, we expect that we have implicitly created two number displays for the hours and minutes. However, as writers of the ClockDisplay class, we have to make this happen. To do this, we simply write code in the constructor of the ClockDisplay that creates and stores two NumberDisplay objects. Because the constructor is automatically executed when a ClockDisplay object is created, the NumberDisplay objects will automatically be created at the same time. And here is the code of the ClockDisplay constructor that makes this work. Each of the first two lines in the constructor creates a new NumberDisplay object and assigns it to a variable. The syntax of an operation to create a new object is new class name, and then in brackets, parameter list. The new operation does two things. First, it creates a new object of the named class, and here that's NumberDisplay. And then secondly, it executes the constructor of that class. If the constructor of the class is defined to have parameters, then the actual parameters must be supplied in the new statement. For instance, the constructor of the class NumberDisplay was defined to expect a single integer parameter, as we can see here. Thus, the new operation for the NumberDisplay class, which calls this constructor, must provide one actual parameter of type int to match the defined constructor header. And this is the same as for methods discussed previously in section 2.5. So with this constructor, we've achieved what we wanted. If someone creates a ClockDisplay object, then the ClockDisplay constructor will automatically execute and create two NumberDisplay objects. From the point of view of a user of the ClockDisplay class, the creation of the NumberDisplay objects is implicit. However, from the writer's point of view, the creation is explicit because they have to write the code to make it happen. And the final statement in the constructor is a call to the updateDisplay method that sets up the display string field. For further information, this call is explained in section 3.12. But now, the ClockDisplay is ready to go. You might have noticed when you created a ClockDisplay object that the pop-up menu offered to you two ways to do that. This is because the ClockDisplay class contains two constructors. What they provide are alternative ways of initializing a ClockDisplay object. If the constructor with no parameters is used, then the starting time displayed on the clock will be 00:00. If, on the other hand, you want to have a different starting time, you can set that up by using the second constructor. It is common for class definitions to contain alternative versions of constructors or methods that provide various ways of achieving a particular task via their distinctive sets of parameters. And this is known as overloading a constructor or method. The last line of the first ClockDisplay constructor consists of the statement updateDisplay. This statement is a method call. And as we've seen before, the ClockDisplay class has a method with the following signature. And the method call invokes this method because this method is in the same class as the call of the method. We also call it the internal method call. Internal method calls have the syntax method name and then in brackets parameter list. An internal method call does not have a variable name and a dot before the method name, which you will have observed in all of the method calls recorded in the terminal window. A variable is not needed because with an internal method call, an object calls the method on itself. We contrast internal and external method calls in the next section. So in our example, the method does not have any parameters, so the parameter list is empty. This is signified by the pair of parentheses with nothing between them. When a method call is encountered, the matching method is executed, and the execution returns to the method call and continues at the next statement after the call. For a method signature to match the method call, both the name and the parameter list of the method must match. Here, both parameter lists are empty, so they match. This need to match against both method name and parameter lists is important, because there may be more than one method of the same name in the class, if, for example, that method is overloaded. And in our example, the purpose of this method call is to update the display string. After the two number displays have been created, the display string is set to show the time indicated by the number display objects. And the implementation of the update display method will be discussed in the next section. Now, let's examine the next method, time tick. And here we see the definition. Were this display connected to a real clock, this method would be called once every 60 seconds by the electronic timer of the clock. But for now, we just call it ourselves to test the display. And when the timeTick method is called, it first executes the statement minutes.increment. This statement calls the increment method of the minutes object. Thus, when one of the methods of the ClockDisplay object is called, it in turn calls a method of another object to do part of the task. A method call to a method of another object is referred to as an external method call. The syntax of an external method call is object.methodName and in brackets parameter list. This syntax is known as dot notation. It consists of an object name, a dot, the method name, and the parameters for the call. It is particularly important to note that we use the name of an object here and not the name of a class. We use the name minutes rather than the number display. The difference between internal and external method calls is clear. The presence of an object name followed by a dot tells us that the method being called is part of another object. So in the timeTick method, the ClockDisplay object is asking the NumberDisplay objects to carry out part of the overall task. In other words, responsibility for the overall timekeeping task is divided up between the ClockDisplay class and the NumberDisplay class. This is a practical illustration of the divide and conquer principle that we referred to earlier when we discussed abstraction. The timeTick method has an if statement to check whether the hours should also be incremented. As part of the condition in the if statement, it calls another method of the minutes object, getValue. This method returns the current value of the minutes. If that value is 0, then we know that the display just rolled over and we should increment the hours. That is exactly what this code does. However, if the value of minutes is not 0, then we're done. We do not have to change the hours in that case. Thus, the if statement does not need an else part. We should now be able to understand the three remaining methods of the ClockDisplay class. The method setTime takes two parameters, the hour and the minute, and sets the clock to the specified time. Looking at the method body, we can see that it does so by calling the setValue methods on both number displays. the one for the hours and the one for the minutes. And then it calls the updateDisplay method to update the display string accordingly, just as the constructor does. Next, the getTime method is trivial. It just returns the current display string. And because we always keep the display string up to date, this is all there is to do. And finally, the updateDisplay method is responsible for updating the display string so that the string correctly reflects the time as represented by the two NumberDisplay objects. It is called every time the time of the clock changes. Once again, it illustrates external method calls. It works by calling the getDisplayValue methods of each of the NumberDisplay objects. These methods return the values of each separate NumberDisplay. And the updateDisplay method then uses the string concatenation to join these two values, separated by a colon, but into a single string. It is worth looking for a minute at the way that this example uses abstraction to divide the problem into smaller parts. Looking at the source code for the class ClockDisplay, you will notice that we just create a NumberDisplay object without being particularly interested in what that object looks like internally. We then call methods such as increment and getValue of that object to make it work for us. So at this level, we simply assume that the increment method will correctly increment the display's value without being concerned about how it does it. In real-world projects, these different classes are often written by different people. You might already have noticed that these two people have to agree on what the method signatures of the class should have and what they should do. And then one person can concentrate on implementing the methods, whilst the other person just has to use them. And the set of methods of an object makes available to other objects is called its interface. And we shall discuss interfaces in much more detail later on in this book. But for now, have a go at the following exercises to test your understanding of this project. And now you've had a go at some of these exercises, let's continue. We shall now examine the same concepts with a different example, using different tools. And we're still concerned with understanding how objects create other objects and how objects call each other's methods. In the first half of this chapter, we have used the most fundamental technique to analyze a given program, code reading. The ability to read and understand source code is one of the most essential skills of a software developer, and we'll need to apply it in every project that we work on. However, sometimes it's beneficial to use additional tools in order to help us gain a deeper understanding about how a program executes. And one tool that we're now going to take a look at is the debugger. A debugger is a program that lets programmers execute an application one step at a time. It typically provides functions to stop and start a program at selected points in the source code and to examine the values of variables. Errors in computer programs are often known as bugs. Thus, programs that help the removal of errors are known as debuggers. It's not entirely clear where the term bug comes from. There is a famous case of what is known as the first computer bug, which actually turned out to be a real bug, a moth, in fact, which was found inside the Mark II computer by Grace Murray Hopper, an early computer pioneer, in 1945. A logbook still exists in the National Museum of American History at the Smithsonian Institute that shows an entry with this moth taped into the book, and the remark, "the first actual case of a bug being found." The wording, however, suggests that the term bug had already been in use before this real one had caused trouble in the Mark II. But fast forwarding to modern day, debuggers vary widely in complexity. Those intended for professional developers have a large number of functions for sophisticated examination of many facets of an application. But BlueJ has a built-in debugger that is much simpler. We can use it to stop our program, step through it one line of code at a time, and examine the values of our variables. Despite the debugger's apparent lack of sophistication, this is enough to give us a great deal of information. So before we start experimenting with the debugger, we're going to take a look at the example which we're going to use for debugging, which is a simulation of an email system. So let's start by investigating the functionality of the mail system project. At this stage, it's not important to read the source code, but mainly to execute the existing project to get an understanding of what it does. Examining the mail system project, we see that it has three classes: mail server, mail client, and mail item. One mail server object must be created that is used by all mail clients. It handles the exchange of messages. Several mail client objects can be created, and every mail client has an associated username. The mail items can be sent from one mail client to another via a method in the mail client class. Mail items can also be received from the mail client from a server one at a time, using a method in the mail client. And finally, the mail item class is never explicitly instantiated by the user. It is used internally in the mail clients and server to create, store, and exchange messages. The three classes have differing degrees of complexity. Mail item is fairly trivial, so we're only going to discuss one small detail. But in contrast, mail server is quite complex at this stage because it makes use of concepts discussed much later in the book. We're not going to investigate that class in much detail here, but instead we just trust that it does its job. Another example of the way abstraction is used to hide the detail that we don't need to be aware of. The mail client class is the most interesting, and here we're going to examine that in some detail. The only section we will discuss from the mail item class is the constructor. It uses a Java constructor that we have not encountered before. The new Java feature in this code fragment is the use of the this keyword. The whole line is an assignment statement. It assigns the value on the right-hand side, from, to the variable on the left, this.from. The reason for using this construct is that we have a situation known as name overloading, the same name being used for two different entities. The class contains three fields named from, to, and message, and the constructor has three parameters, also named from, to, and message. So while we're executing the constructor, how many variables exist? The answer is 6, 3 fields and 3 parameters. It's important to understand that the fields and the parameters are separate variables that exist independently of each other, even though they share similar names. A parameter and a field sharing a same name is not really a problem in Java. The problem we do have, though, is how to reference 6 variables so as to be able to distinguish between the two sets. If we simply use the variable name from in the constructor, for example in the statement system.out.println from, which variable will be used, the parameter or the field? The Java specification answers this question. It specifies that the definition originating in the closest enclosing block will always be used. Because the from parameter is defined in the constructor and the from field is defined in the class, the parameter will be used because its definition is closer to the statement that uses it. Now all we need is a mechanism to access a field when there is a more closely defined variable with the same name. That is what the this keyword is used for. The expression this refers to the current object. Writing this.from refers to the from field in the current object. Thus, the construct gives us a means to refer to the field instead of the parameter with the same name. Now, we can read the assignment statement again. This.from equals from. This statement, as we see now, has the following effect. field named from equals parameter named from. In other words, it assigns the value from the parameter to the field with the same name. This, of course, is exactly what we need to do to be able to initialize the object properly. One last question remains. Why are we doing this at all? The whole problem could easily be avoided just by giving the fields and the parameters different names. The reason is the readability of source code. Sometimes there is one name that perfectly describes the use of a variable. It fits so well that we don't want to invent a different name for it. We want to use it for the parameter, where it serves as a hint to the caller, indicating what needs to be passed. We also want to use it for the field, where it is useful as a reminder for the implementer of the class, indicating what the field is used for. If one name perfectly describes the use, it's reasonable to use it for both and go through the trouble of using the this keyword in the assignment to resolve the name conflict. The most interesting class in the mail system example is the mail client. We shall now investigate it in more detail by using the debugger. The mail client has three methods: get next mail item, print next mail item, and send mail item. We will first investigate the print next mail item method. And before we start the debugger, set up a scenario that we can use to investigate. So have a go at this exercise here. And after you've set up the scenario in this exercise, we have a situation where one mail item is stored on the server for Juan, waiting to be picked up. We have seen that the print next mail item method picks up this mail item and prints it to the terminal. And now we're going to investigate exactly how that works. To start our investigation, we set up a breakpoint. A breakpoint is a flag attached to a line of source code that will stop the execution of a method at that point when it's reached. It's represented in the BlueJ editor as a small stop sign, as we can see here. You can set a breakpoint by opening the BlueJ editor, selecting an appropriate line, which in our case is the first line of the print next mail item method, and then selecting the set/clear breakpoint from the tools menu in the editor. Or alternatively, you could also simply click into the area next to the line of code where the breakpoint symbol appears to set or clear breakpoints. But note that the class has to be compiled to be able to do this. And once you've set a breakpoint, invoke the print next mail item method on Juan's mail client. The editor window for the mail client class and the debugger window will pop up, as illustrated here. And along the bottom of the debugger window are some control buttons. They can be used to continue or to interrupt the execution of the program. And for a more detailed explanation of the debugger controls, refer to Appendix F. But on the right-hand side of the debugger window are three areas for variable display, titled Static Variables, Instance Variables, and Local Variables. We're going to ignore the static variable area for now, as this class doesn't have any, and we'll actually come back to this later and discuss it in further detail then. So we can see that this object has two instance variables, or fields, which are server and user, and we can also see their current values. The user variable stores the string Juan, and the server variable stores the reference to another object. And the object reference is what we've drawn as the arrow in object diagrams. Note that there is no local variable yet. This is because the execution stops before the line with the breakpoint is executed. Because the line with the breakpoint contains the declaration of the only local variable, and that line has not yet been executed, no local variables exist at the moment. The debugger not only allows us to interrupt the execution of the program so that we can inspect the variables, it also allows us to step forward through the program slowly. When stopped at a breakpoint, clicking the Step button executes a single line of code and then stops again. The result of executing the first line of the printNextMailItem method is shown here. We can see that the execution has moved on by one line. Note that the small black arrow next to the line of source code indicates the current position. And the local variable list in the debugger window indicates that a local variable item has been created and an object assigned to it. We can now use the step button repeatedly to step through to the end of the method. This allows us to see the path the execution takes. And this is especially interesting in conditional statements, where we can clearly see which branch of an if statement is executed and use this to see whether it matches our expectations. When stepping through the printNextMailItem method, we have seen two method calls to objects of our own classes. And this line here includes a call to the getNextMailItem method of the server object. Checking the instance variable declarations, we can see that the server object is declared of the class mailServer. And the line item.print calls the print method of the item object. We can see in the first line of the printNextMailItem method that the item is declared to be of the class mailItem. Using the step command in the debugger, we have used abstraction. We viewed the print method of the item class as a single instruction, and we could observe that its effect is to print out the details, such as sender, recipient, and message, of the mail item. If we're interested in more detail, we can look further into the process and see the print method itself execute step by step. And this is done by using the step into command in the debugger instead of the step command. Step into will step into the method being called and stop at the first line inside that method. In the experiments of the previous section, we have seen another example of object interaction similar to the one that we've seen before, objects calling methods of other objects. In the printNextMailItem method, the mail client object made a call to the mail server object to retrieve the next mail item, and this method, getNextMailItem, returned a value, an object of type mailItem. Then there was the call to the print method of the mail item, and using abstraction, we can view the print method as a single command. Or, if we're interested in more detail, we can go to a lower level of abstraction and look inside the print method. In a similar style, we can use the debugger to observe one object creating another. The sendMessage method in the mailClient class shows a good example. In this method, a mailItem object is created in the first line of the code, as shown here. The idea is that the mailItem is used to encapsulate a mail message. The mailItem contains information about the sender, the recipient, and the message itself. And when sending a message, a mail client receives the mailItem with all of this information. And when sending a message, the mail client creates a mail item with all of this information and then stores the mail item on the mail server. There, it can be later picked up by the mail client of the recipient. And in the line of code shown here, we see the new keyword being used to create a new object, and we see the parameters being passed to the constructor. Remember, constructing an object does two things. The object is being created and the constructor is executed. Calling the constructor works in a very similar fashion to calling methods. This can be observed by using the step into command at the line where the object is being constructed. So in summary, in Chapter 3, we've discussed how a problem can be divided into subproblems. We can try and identify subcomponents in those objects that we want to model, and then implement subcomponents as independent classes. Doing so helps in reducing the complexity of implementing larger applications, because it enables us to implement, test, and maintain individual classes separately. We have seen how this approach results in structures of objects working together to solve a common task. Objects can create other objects, and they can invoke each other's methods. So understanding these object interactions is essential in planning, implementing, and debugging applications. And we can use pen and paper diagrams, code reading, and debuggers to investigate how an application executes or to track down bugs. So have a go at the following exercises then to test your understanding of the concepts introduced in this chapter.